So can you see the board? Can you see
Yes,
the board?
sir. Yes,
Okay.
sir.
Okay. So in the so what we are doing basically, I will just recapitulate. Okay. So we are defining, we are trying to write the expression for Lorentz transformation in terms of the generators. Okay. So generators are operators or entities, okay, which generates the corresponding transformation. In this case, the Lorentz transformation. So what do you mean by generates? Okay, so if you specify generators and parameters, okay, parameters of transformation, then your transformation is fixed. So one can prescribe, one can write down the given transformation in terms of minimal set of quantities. Okay, and that minimal set is this generator. Okay, so I will maybe it's better if I go back. Yeah. Okay. So here, yeah. So lambda maybe yeah. This is better. Huh? So any Lorentz transformation, any infinitesimal Lorentz transformation, one can write the expression near identity in terms of these J mu nus, and this J mu nu for each mu and for each nu, this J mu nu represents a matrix. Okay. So this is 4 cross 4 matrix. So it is the, we are in the coordinate representation still. Okay, we have not gone into field representation or state representation. Okay, so in the coordinate representation, the infinitesimal Lorentz transformation can be written down near the identity in terms of these generators. For each mu and for each nu, these J represent 4 cross 4 matrix. Okay, and the fact that this transformation leaves the line element invariant, okay, lead to the antisymmetry between mu and nu. Okay, so these J mu nus are antisymmetric in mu and nu. Okay, not as a matrix. Okay, not as a in the entries of matrices. Okay, this J01 is 4 cross 4 matrix. Okay, if I write J10, then that is itself is a 4 cross 4 matrix. So these 0 and this 1, they are not, they do not represent the entries of this J matrix. This 01 itself is a matrix. J01 itself is a matrix. Similarly, J02, J03, etc. Okay, so the antisymmetry between omega, this mu nu here, okay, tells us that we have 6 parameters. And corresponding to 6 parameters, I have 6 generators, this one and these 3. This lambda omega is 4 cross 4 matrix. Its munith entry is munith entry of this expression. The munith entry of identity is just a delta mu nu. Okay, and munith entry of this is munith entry of this J mu nu matrix, or maybe rho sigma entries of J mu nu matrix. Okay, clear? So if we know what are these J's, okay, then we know is lambda omega. And omega here involves the boost as well as the rotation. Why we are taking rotation into Lorentz transformation? Because boost and rotation represents most general Lorentz transformation. Because what is the definition of Lorentz transformation? The transformation which leaves the 4 element invariant, the line element invariant, right? Okay, so we know that the boost preserves the line element, but also the rotation, because if we rotate in xy plane or in yz plane or zx plane, we are not going to change the line element. Okay, so rotation obviously is the Lorentz transformation. So for example, rotation in XY plane is also a Lorentz transformation. Okay, so it is a sub part of Lorentz transformation. Okay, fine. So the omega here is a collective label which involves boost as well as rotation. And now we can check. Okay, so all these factors are arranged in such a way that you should get our original Lorentz transformation. Okay, so if you so this is the infinitesimal version. Okay, so if you want to write down the finite Lorentz transformation, okay, from this, okay, from this, okay, you have to apply that n times and take n tends to infinity. Okay, and this omega mu tends to 0. Okay, clear? So in that limit, you recover the finite Lorentz transformations. Okay, and we have seen that with these factors, all these factors are in place. Okay, we get the familiar Lorentz transformations, boost and rotation. Okay, finite version of Lorentz transformation. Okay, so that we have already seen. So maybe I will just. So here, not here also. Yeah. So before I go and revise other things, okay. Another thing about this J is that one can give a representation to these generators. Okay, so munith entry of J rho sigma is this. Okay, so one can write in terms of eta matrix and chronicle delta. Okay, so now you can fix rho and sigma with different indices. Okay, and you will get the corresponding entry of that generator, corresponding entry of that matrix generator, matrix form of that generator. Okay, so here, for example, so J01 is this matrix. Okay, similarly, you can write expression for J02, J03, etc. Now you can use these matrices, okay, to determine, to verify the consistency with our previous result. Okay, our starting point, special relativity. Okay, so you consider the boost along x direction. Okay, and you consider the infinitesimal boost. Okay, then we know from our earlier expression of Lorentz transformations, okay, we can calculate the infinitesimal change in certain coordinate. Okay, delta x, infinitesimal change in that coordinate. Okay, and you write that is this. Okay, then you write that same change in terms of generator. Okay, so you should know all these generators J01, J12, J23, etc. Okay, you can use them and you can get the corresponding change in the coordinate. Okay, and uh, we can verify that this delta x0 is eta1 x1. Okay, right. So eta1 is basically the parameter for boost. I have set some. I have somewhere we have mentioned expression for eta. Yeah, I have mentioned here. Yeah, eta. Yeah. Okay. So this represents the boost along x1 direction. Okay. Similarly, we have eta2 and eta3. Okay. Note that this eta runs from 0 to infinity because v is less than or equal to c. Okay. So we have eta1, eta2, eta3. Okay, and theta1, theta2, theta3. Okay, those theta represents rotation and these etas represents boosts. But there is a relationship between omegas and etas. Okay, that I'm trying to find. Okay, yeah. So omega, yeah, omega 10 is set to eta 1. Omega 12 will be eta 2. Omega 13 will be eta 3. Okay, clear? And so on. Okay, but because of antisymmetry in omega, you can determine all the other. If you know 10, then you can determine omega 01, etc. Okay, so one can determine omegas in terms of etas. Okay, then one can use that here, expressions like this, and check the validity of this. That is what we have done. Okay, but before doing this, you should calculate all these matrices. Okay, then you will get this, because in general this is just delta x0. Similarly, you can calculate delta x1, delta x2, delta x3, etc. Okay, for a given transformation. So here, what is the transformation? Here it is the boost along x1 direction. I can take boost along x2 direction, boost along x3 direction. I can take rotation in x1, x2 plane, rotation in x1, x3 plane, and so on. Okay, for in each case, these parameters will be different. So you have to use different jets. Okay, so you should know all these jets. Okay, fine. Then another thing is, which will require in future, is the commutation relation. What is the algebra satisfied by these generators? That decides that reflects in the representation of the Lorentz transformation. Okay, so the algebra means the commutation relation among these j alpha betas. That is important. Okay, and the commutation relation between j alpha beta. Okay, so the commutator between j mu nu j rho sigma. Okay, is okay. So commutation relation between j mu nu and j rho sigma is this. Okay, we have obtained this relation. Okay, for all mu nu and for all rho sigma. Okay, fine. Now we want some simplification in that. Okay, in this result. We want some simplification. Okay, so now we will define three generators, and we will call them as j hat. Okay, and we define another three generators k. Okay, k1, k2, k3. Okay, they are related. Obviously, they should be related with this j mu nu. Okay, so we have this j mu nu. That is what we obtained so far. Okay, just a minute. So it is something is happening. Yeah, we have this j mu nu object. Okay, from this j mu nu, okay, we define ji and ki. Okay, I runs from 1, 2, and 3. Now, how ji is defined? Ji is defined by taking only spatial indices of j mu nu. Okay, so ji is a 3 vector. Basically, you will see that this ji is kind of 3 vector. How it is defined? It is half of epsilon ijk. It is usual 3-dimensional Levi-Civita symbol. Okay, Levi-Civita symbol in 3 dimension. Okay, and jk. So half epsilon ijk jk. So these jk indices are contracted. Okay, so this behaves as a 3 vector. We will see that. The commutation relation, you can use the commutation relation between j mu nu j rho sigma to determine the commutation relation between Ji and Jj. Okay, and it turns out to be this. So this is the commutation relation between Ji Jj, Ji Kj, and Ki Kj. Okay, fine. So this is basically another form of Lorentz algebra, or algebra of generators of Lorentz group. Okay, Lorentz group is basically SO3, comma. Okay, so here we can see that combination of two rotation gives you the rotation. Okay, combination of two rotations gives you the rotation. Combination of boost and rotation will not give you the rotation, it gives you the boost, and combination of two boosts, okay, gives you the rotation. Okay, so you can see from here that rotation by themselves, you can just see from here, okay, rotation by themselves form a subgroup. Why it is subgroup? Okay, because if I consider two rotations, I will get a rotation, so it is a closed. Okay, so rotations, two successive rotation gives you the rotation. Okay, so if I consider the collection of rotations, collection of all the transformations which are Lorentz transformations, but I will restrict that collection to rotation. Okay, that set, that subset is a subgroup. Okay, because if I take any two element in that subset, okay, and if I compose, I will get a element in that subset. So that subset by itself is a subgroup. However, the another part, that is the, suppose if I consider set of all boosts, okay, that does not form a subgroup, because if I combine two boosts, I may get an element which is outside of that set. Okay, because here we are seeing that the combination of boost generators gives you the rotation generator. So it may happen that if I apply two successive boosts, I may get rotation. Okay, hence the boost part does not form subgroup. Okay, but still it is an element of Lorentz group. Okay, eh, boosts are by themselves belong to Lorentz group. But all set of all boosts does not form a subgroup of Lorentz group. Like unlike this, unlike the rotation. Okay, so that is the import. That is the main difference. Fine. So this is what our final result. Okay, so the commutation relation among the generators of Lorentz transformations. Okay, now we can simplify it even further, okay, and write. So okay, so in terms of these J's and K's, okay, your Lorentz transformation can be written in this form. Okay, so here theta dot J, okay, theta dot J means this is nothing but theta n cap. Okay, so this is the direction in space. Okay, this is the angle through which you are rotating about this n cap dot J. Okay, so this is the shorthand for this. Okay, here. Okay, but there are n cap. So there is so n cap is basically n1, n2, n3. Okay, like your I cap, j cap, k cap. Okay, so n1, n2, n3. So sometime in some textbook they write theta n1 as theta 1. Okay, theta n2 as theta 2 and theta n3 as theta 3. Okay, clear? So this is understood when I write this. Okay, so it is theta 1 j1 plus theta 2 j2 plus theta 3 j3, where theta 1 is basically n1 theta, n2 and theta 2 is n2 theta, and so on. Okay, yeah, and similarly here eta dot k. Okay, so eta is basically your eta 1 is that tan hyperbolic v1 by c. Eta 2 is tan hyperbolic v2 by c, and etc. and so on. Hmm? Clear? Hmm? Yeah. So here I have defined clearly what the relation between etas and omegas. Okay. So omega I0 is eta I. Okay, and this theta k is basically omega ij epsilon ijk. Okay. So if I know these thetas and etas, I can calculate omegas, all these omegas. Hmm. Okay. So it works in both ways. Sometime I may use Lorentz. I may write Lorentz transformation in terms of omegas. Sometime I may use this relation. Both are equivalent. It's just a different way of writing our previous expression. This one. Hmm? It's just a different way of writing this expression. Where is that? Yeah, this expression. Okay, this is the infinitesimal form. Finite form will be e to the power minus I by 2 omega mu nu j mu nu. Okay, that will be a finite form. Okay, that you can compare with this result. Okay, with this result. Okay, so in our earlier form, if I want to write Lorentz transformation, then it would be e to the power minus I by 2. Okay, omega mu nu j mu nu. Okay, so these two are equivalent. The same thing. Okay, remember we are just restricting ourselves to the representation of Lorentz transformation, the coordinate representation of Lorentz transformation. Okay, I can uh, I can say that this is not at all required. Okay, you can directly work with our original good old Lorentz transformations and rotations. Okay, this juggler is not important. If I want to restrict myself to classical physics. Okay. But now when we go to quantum mechanics, we have to see different representation of the Lorentz transformations. Different representations of Lorentz transformations. And there we need this form. Okay. We cannot just talk in terms of coordinates. Okay, we have to see how to represent the Lorentz transformation in the space of states, quantum mechanical states. Similarly, we need to find how to represent Lorentz transformation in the space of fields. etc. Okay, there we need to write to talk about generators and parameters. Okay, I repeat, this Lorentz transformation is still in the we are still in the coordinate space. Okay, what do I mean by that? This will act on the four coordinates. Okay, see, this is the 4 cross 4 matrix. This lambda omega is basically 4 cross 4 matrix. Okay, so lambda omega is 4 cross 4 matrix. It will act on 4 vector, 4 coordinate vector. Coordinate, basically it is not a correct way of writing. Coordinate 4 vector. Okay. Okay. What are the constituents of lambda omega? Lambda omega requires parameters, that is omega mu nu. Okay, there are 6 parameters. Okay, and J mu nu, 6 generators. Okay, so if you give me J mu nu and if you tell me what Lorentz transformation you are looking at, okay, I know this matrix and then I know how the coordinate changes. Okay, so this lambda omega will act on x, okay, your coordinates. Okay, it will give you x prime. Okay, clear? But I don't know how it acts on, say, for example, Klein-Gordon wave function phi. I don't know how lambda omega acts, or I don't know how it acts on Dirac spinor. This is the 4 component object. Okay, I don't know this. So now we have to begin our study of representing the Lorentz transformation, representations of Lorentz transformation, different representations of Lorentz transformation. And as you can guess, the study of Lorentz transformation requires study of or knowledge about representation of rotation. So this plays an important role. Okay, that's why I told you to go through Sakurai chapter 3, modern quantum mechanics. Okay. So I hope you have completed those sections. Am I correct in assuming that?
Yes, sir.
Yes, sir.
Okay, then I will from henceforth I will assume that. Okay, so there should not be any confusion in writing the rotation in terms of Euler angles or axis angle parameters. Okay, you should be able to figure out, okay, what parameters I am using, etc. Clear? Okay. It's not that I will completely skip that part. Okay, I will highlight some essential features. Okay, but I will not concentrate on that. Okay, I will not spend great deal of time on rotation. Okay, but still I need to motivate from rotation. So I have to discuss some important points. Okay, fine. So this is just revision of our previous 2-3 classes. Okay, and now the plan is that now I will discuss the representations of Lorentz group. Okay, then I will see how Dirac equation comes from this point of view, from group theory point of view. Okay, and then we will go to fields. Okay, but you must understand that I have skipped so many topics from relativistic quantum mechanics. Okay, for example, the solution of Dirac equation in central force field, solution of Klein-Gordon equation in central force field. Okay, what is the energy spectrum? Okay, central force field, I mean the hydrogen atom. Okay, so what is the energy spectrum for Dirac hydrogen atom? Okay, etc. That I have completely skipped. Okay, also there are other interesting effects. For example, is the the effect or the effect of negative energy solution in okay, so that is known as Zitterweg. Okay, that I have also skipped. Okay, and in this semester also I won't be able to take that because then will be lagging in field theory. Okay, so what I will do, I will give the central force problem for Klein-Gordon as well as Dirac equation as a lab exercise. Okay, and then I will give some part of group theory as a lab exercise. Okay, so in this semester you have to work hard. Hmm? Okay. Okay. And so after finishing this representation theory of Lorentz group, okay, we will move to the field theory. Okay, there I will start from the scratch. Hmm? Okay, fine. And now regarding the timing, okay, so we will set timing. So which time you prefer? When is your
This
STTP class according to timetable?
uh, STTP is from 11:30 to 1.
1.5 hour STTP?
Yes, Muhuri sir engages that time. He has
Okay,
already
so
started.
he's taking 1.5 hour. Okay, so 11:30 to 1, and which days?
Monday, Wednesday, and Friday, I think. Can somebody please correct me if I'm wrong?
Can someone correct him?
Sir, I'll just a minute. I'll check it from the group.
Just check. So it's not with me, I think. It is, I don't know. I missed that message. Anyway, have you found out?
Yeah, it is from Monday to Thursday, uh, as per official timetable.
STTP.
Yeah, from Monday to Thursday, from 11:30.
But is there any difference between official timing and
No,
actual
as
days?
as per the official timetable, it should be from 11:30 to 12:30, and
Uh,
sir is, I think, taking for 1.5 hours. So
Correct.
he's
No,
extending for
timing, but days I'm saying.
no days. It is from Monday to Thursday.
Officially as well as unofficially, right?
Yeah, officially as well as unofficially.
Okay, so we will take from maybe uh, So afternoon, what is the situation in the afternoon?
Sir, Monday and Wednesday, as per the official timetable, nuclear physics tutorials will be there.
Nuclear physics tutorials will be there. Okay.
Monday and Wednesday.
Monday and Wednesday. 2 days.
There are two groups, so depending on that, I think one group
So
will be
you will be in one group, right? So either Monday or Tuesday.
Monday or Wednesday.
Monday or Wednesday. Either Monday or Wednesday. So you will be in one of them. So we will take Thursday, Wednesday, Thursday, Friday, or Wednesday, Friday, and Saturday. Is that fine?
Okay, sir.
Okay. Wednesday, Friday, and Saturday. That would be okay, I think. And so Friday and Saturday, there is nothing in the afternoon, right?
No, sir. Just the project and advanced lab, I think.
Just the
Project
project.
discussion.
Okay, so advanced lab, I will be the one who will be conducting that advanced lab. Okay, so we will meet. So let me. Okay, so let me go through again. I will think, and then we will take 3 days in a week, 3 or 2 days. If I take 2 days, then I will take 2 hours, 2.5 hour something. Okay, we will see that. So either 2 days or 3 days in a week, I will take. Hmm? Okay, today I will post that message. Okay, so in this week, I may not take any further lectures, but next week onwards we'll start regularly. Okay.
Okay, sir.
Okay, but anyway, I will post it on the group. Okay, time and etc. Okay,
Okay, sir.
and
Sir, most
those who are doing project under me, so we have to meet once. Okay, all the project students, I need to discuss with them. So in the next week, I will set the time. We will meet. Okay, fine. So I am closing down this meeting. Any query or question?